Hello, I'm Hatt, and welcome to our video today about water wall slag formation in pulverized coal plants. This is a subject that I've covered for almost 40 years, and I'm here to tell you that I haven't been able to solve it, but I have seen a lot of factors, both in the combustion tuning of the plant and with fuel qualities, that influence this phenomena. I wanted to start with the basic nature of coal. In other words, the coal itself has some ash, but during the mining process, you're going to get some other ash mixed in. This is for raw coal products, which most our subbituminous and strip mine coals are. If we wash the coal, we eliminate this issue. But most of the coals that are economical that we'll be using will be raw coals and therefore can have fluctuating ash levels at any given point. Now what they do is they anticipate this and they give you an average ash spec that includes some of that ash, but what we don't see is necessarily up inside the up and down of the ash levels. And so this was just a picture I saw that sure enough it looks like a little ash fell into the coal. The miner doesn't necessarily have to take this, but if it did take this ash that fell into the coal, my question is is that the type of material that might cause slag or influence slags? So I just want you to know that like this sort of occurrence happens all the time at the coal mines, but they doesn't necessarily show up on the average ASTM type analysis where we're looking at 10,000 or 15,000 ton lot sizes, which doesn't give us much resolution for looking at these issues. Another phenomena that has occurred is that the material or the ashes that are associated with the coal tend to be low fusion or things that lower fusions. Calcium, sodium, iron come to mind. And then the out of seam dilution or the rock material that might get mixed in with the coal tends to be higher fusion material. And so again, you see a fluctuation of the fusions. But I'm just going to suggest that when you put more ash into a coal, you didn't take any of the low fusion material away. You diluted it with some other material that it could indeed melt or incorporate into a slag deposit. We typically use ash fusion temperatures to look at the melting or slagging properties of a coal. The first thing I do is I ask you, why are you using ash fusions? Why are you using ash fusions? Ash fusions actually represent a stoker-fired boiler, and the technology is from the 1920s, so it's at least 100 years old. It is a physical test, which gives us some benefit, but basically ash fusions is designed for a stoker-fired furnace, not the pulverized coal plants that we use today. So throughout the day, the power plant operator might actually see a variety of coals hit the furnace. And if he were to take a sample of all that coal during the day, the average of the coal might actually be below the plant limit. But what about this little hump that goes over the plant limit? That could be a slag, pollution, something that causes a derate, or costs the power plant money. But when we look at the coal quality information, it's not there. Now, we never show you these ugly pictures of the ash fusion temperature. We always show you a much better looking picture of the ash fusion or the cone meltdown tests, because at different points along this melting down of the cone, we call those the different fusion temperatures. So the initial deformation is where something first occurs. The softening temperature is where the height equals the width of the material. When the height is only half the width, that's the hemispherical temperature, and then it goes flat, we're going to call that the fluid temperature. One of the good things about the fusion test is that it is run in an oven, so we can therefore vary the atmosphere in the oven to look at both reducing and oxidizing conditions. We tend to get lower fusions in the reducing or poor combustion or maybe even low NOx firing that we might be doing. So I look for high CO as potentially causing some slags. What I thought I could do is just briefly give you some visual diagrams of some of the mechanisms that I see with water wall slag formation. So the first picture I'm showing you is a particle of coal that when it comes out of the pulverizer devolatilizes, loses its moisture, and begins to burn and eventually ends up as CO2. What I'm worried about is mineral matter like pyrites not grinding up as fine as the coal, coming out of the pulverizer and continuing the trajectory through the flame, melting, and hitting the wall in a sticky or wet formation. When I first drew this picture about 10 years ago, I put the word splat on it, and we'll talk about the rod hat splat factor a little bit later. But this concept of the mineral matter hitting the wall after passing through the flame, because of its large size and high momentum or kinetic energy, keeps it going towards the wall as opposed to heading towards the boiler outlet or becoming fly ash. Now with bituminous coals, to make sure that the combustion is suitable and the carbon in the ash or the LOI isn't too high, we tend to keep the mill fineness pretty tight because the bituminous coal doesn't burn very well in a large particle size. So with bituminous coal people, we can have the problem, but I mostly see the problem with particle sizing coming from the subbituminous coal users. The subbituminous coal users they need more throughput of tons through the mill, so not grinding as fine actually adds capacity to the mill. If you look at the carbon in the ash or the LOI from a subbituminous coal, it could be very low even if the sizing is not quite right. That's a particular concern when you have good LOI or low carbon in the ash, and yet the pulverizer is making wall slags because the fineness is not right. So that's with subbituminous coals. So that's one of the things we have to trust our judgment and our data from the coal mill fineness results is we might want to use those to guide us rather than the LOI number to look at the performance of pulverizers when using subbituminous coals, particularly if you're having heavy wall slags. The problem comes in when we either have a high sulfur subbituminous coal and or mixing a higher sulfur coal or bituminous coal with a subbituminous coal. We can get into a situation where the carbon in the ash still looks good from the subbituminous component, but we're getting additional wall slags from a pyritic or sulfur component from the coal. Another situation we get into with the subbituminous coals is the walls might actually be wet in nature due to the low fusion properties of the coal itself. And then when we have that out-of-seam dilution or that rock type material come in, particularly like silicates or quartz, they don't grind up very, very well because they're hard in nature. And then they go, not unlike the pyrite, they go in the direction that they're pointed from the burner and potentially impact wet slag on the walls, in which case you get a big rapid buildup of slag on the walls, which could fall down and make a problem down in the lower furnace. So what I really wanted you to do is try to grind the mineral matter fine so that you can end up with just dry fly ash leaving the boiler rather than wet slags on the walls. So just keep in mind that if this is the case, you would prefer a higher calorific value coal. The low calorific value coals require quite a bit of coal flow to make the load, and then the corresponding air to fuel ratio is probably set at 1.8 or 2. So we get into a situation where lower calorific value coals are increasing the pipe velocity. There also is the chance that if at higher coal flows, the fineness deteriorates, so you get more coarse particles. So most slag starts on the walls. When a unit is freshly started up or is able to control or shed the wall slags, you might be able to have clean walls, but over time they start growing slags so that you might actually, in a bad situation with low fusion coals, end up with wet walls. And wet walls are particularly good at capturing additional ash that reaches them. So even if it's a dry ash particle, like a quartz particle or high fusion particle, it still sticks in to the slag. And so this is part of the concept of the rod hat splat factor, except if I have a wet wall rather than a wet particle. As the wall slags build up, they impede the heat transfer of the energy from the flame to the walls or the water walls to make steam. And so what we see is an increase in the furnace exit gas temperature. If you get an increase of furnace gas temperature up over the melting point of some of these particles, you start getting the slag deposits up in the superheater, reheater, or the inlet to the convection pass area of the boilers. If you can measure the furnace exit gas temperature, or the FEGT, this gives you a control point to look at whether or not your walls are clean or dirty. Now, if we're not going to use the ash fusion temperatures because of some of the deficiencies that I see with them, what we want to do is look at the ash chemistry, or the major and minor elements in coal ash. So here they are. I've divided them up into two groups. One of them is the silicates, the aluminum silicates, that are more of the rock, high fusion type material. And then there's the pyrites, or the calcium or sodium actually attached to the coal, that tend to be lower fusion materials. So again, the rocks tend to be high fusion, but the stuff that's in the coal tends to be low fusion. Remember that this is not a mineral analysis. Mineral analysis actually include the names of the rocks or minerals, things like pyrites or quartz or the different types of clays. What we get from the ASTM coal laboratory is major and minor elements in the coal ash. Now, the industry, rather than using these terms, uses the terms acids for the silicon, alumina, and then a little bit of titania, and bases for iron, calcium, magnesium, potassium, and sodium. This is useful to understand because over the years, people have looked at the ratio of bases to acids. So basically, you take the sum of the bases and divide it by the sum of the acids. As the base-acid ratio increases, the fusions tend to go down. In other words, there's more fluxing material in there to make the material wetter at a lower temperature. This is what the equation for the base-acid ratio looks like. One of the unique things about iron, and this is where my discussion about the being able to run a fusion temperature in a reducing atmosphere versus an oxidizing atmosphere, one of the things about the element iron is it can burn to two different forms. The actual highly oxidized or fully burnt form is the hematite or rust, the Fe2O3. This actually acts like an acid or helps dry up or raise the fusion temperatures. It's the unburnt form of iron, the FeO, which forms in the presence of carbon monoxide. It's this unburnt iron that makes the wet, drippy, low fusion slags. So in some respect, with higher iron coals, we have to burn the iron. This is also the change in the fusion temperatures that we see between the oxidizing and reducing atmospheres. As illustrated here, you can see that the higher the iron goes, the larger the spread between the oxidizing and reducing fusion temperatures. One of the things that we have to recognize is that low NOx firing generally likes to take the oxygen out of the system and create a high carbon monoxide environment. Not only will carbon monoxide take the oxygen off of iron, it also takes the oxygen off of nitrous oxides. So you can lower NOx by having the presence of carbon monoxide. But this carbon monoxide causes a lot of issues associated with slag and corrosion. Also, if you don't burn the sulfur, you get a sulfide, and you can actually have sulfide attack on your water walls. So just in summary, it's the iron and calcium and sodium that we mostly worry about. They're the low fusion or fluxing type elements. And then the elements like silica and alumina are the rock type materials. One of the things that with the rock materials we might worry about is how much quartz is actually in the rocks. There's a equation developed by Eric Rath that actually tries to estimate the quartz using the silica alumina. It's a very easy equation. You literally just take 1.5 times the alumina and subtract it from the silica, and the remaining SiO2 is deemed quartz or estimated quartz. And so one of the things that ash fusion temperatures and base acid ratios and things like that don't actually incorporate is how much ash there is in the coal. What I'm suggesting is that if you take the same ash quality and double the amount of ash, that you're going to get about double the slag buildup rate, or it builds up twice as fast, which takes away from the operator's time to deal with slag. So I think the amount of ash is an important factor to consider. This is a chart from the 1980s that tried to incorporate the amount of ash along with the base acid ratio and the ash fusion temperatures. And the answer to this graph is a dot in like a low or medium or high slagging factor area of the chart. Unfortunately, this chart is confusing and hard to look at, and if you didn't have the chart in front of you, it would be very hard to explain how you got the result that it was a medium or high slagging coal. But one of the important things to recognize along the y-axis is the fact that it says pounds of ash per million BTUs. So I like the idea that they're looking at the ash in a weight or mass divided by energy unit. So whether it's pounds per million BTU or kilograms per million kilocalories, this is the way we're going to look at ash. And it helps incorporate the fact that as ash goes up, the calorific value goes down. So I'm going to be looking at the pounds of ash or the kilograms of ash per million kilocalories or BTU, depending on the units. And then what I can do is I can multiply it by the decimal percent of the element, and I'll actually get the weight divided by energy of the amount of element, the pounds of sodium going into the unit or the pounds of calcium going into the unit. And if you're in the metric, we'll look at kilograms of material going into the unit per energy value. And this is one of the ways that we can sort of rate the amount of material, not only the amount of ash, but the amount of the problematic elements. In fact, we could look at the amount of things like quartz and pyrites. And that's what we might use for the splat factor calculation. Here's an example of what I'm talking about. There's two coal qualities represented here. One of them is an 8% sodium coal with low ash, and the other is where the mine has added ash to the product, to the coal product. So out-of-seam dilution is added, and it dilutes the percent sodium. So in other words, it's low or it's low sodium material that they're adding to the coal product, so it makes the percent sodium go down. But when I do the math and look at the kilograms of ash per million kilocalories and multiply it by that decimal percent sodium, I see that the final product, the higher ash, lower sodium product, actually has more sodium in it. So by looking at this way, we don't see the percents or the effect of dilution. We actually look at the total material going into the power plant. I think this is a very reasonable way to judge coal quality as to which coals might be causing more or less problems based on more or less of the problematic element or ultimately the mineral or material that's in the coal. So I Googled splat and I came up with this picture of big bugs hitting a windshield on a car. I don't know if I've had an opportunity to have this happen to you. It usually happens at high velocity, in other words, highway speeds and big bugs. And you can almost see that this is one of the things that I'm talking about. High velocity, large particles coming from the pulverizers have an opportunity to hit the wall. If you have a corner-fired boiler, they're probably pointed at a wall. If you have a one wall or front wall fired boiler, they're pointed at the back wall. And if you have the opposed wall boiler, what you'll see is the actual two flames hit each other and then go to the side wall. So we'll see some of these slags and water wall corrosion issues caused by this trajectory of the material. But even on an opposed wall firing unit, usually they hit each other and spread out to the side wall. So there is this opportunity for large particles like pyrite and quartz, because those are the hard to grind material. And then keep in mind that pyrite is about 4 times the density of coal. In other words, the same size pyrite particle has 4 times the mass of the coal particle. The quartz particles and rock particles are only about 2.5 times the density of coal, but still the same size rock material has a larger mass associated with it. So if I apply the kinetic energy equation to these particles, and I like kinetic energy because I'm squaring the velocity In other words, small changes of velocity at the top end because of the parabola behavior of a squared function. Small changes at this top end end up causing a lot more issues because I'm squaring it. In other words, it's double compounding the velocity. So this is where low calorific value coals can hurt the splat factor also. So the final splat factor number takes a number of things into consideration. It looks at the amount of pyrite and quartz that are in the coals. In other words, if you double the sulfur or double the pyrite in a coal, the splat factor is going to be impacted significantly because there's more of that material in the coal. I then take the mass of a 50 mesh particle and I multiply that by the coal pipe velocity. So low BTU coals or high primary airflow can really increase that mill pipe velocity. And remember, I'm squaring that for this equation. So that's an issue. And then I take that whole value and I multiply it by the amount retained on the 50 mesh screen. In other words, when we do a pulverizer fineness testing, we get a percent passing the 50 mesh usually, or sometimes we express it as retained. I would like to see maybe only 0.1 or 0.5% material retained on that 50 mesh. If you have 1 or 2 or 3% remaining on that 50 mesh, I'm multiplying the splat factor by that. So the splat factor would be double with 4% retained on the 50 compared to 2% retained on the 50. And of course the 2% retained on the 50 is maybe 4 times bigger than my 0.5% type recommended number. So just to emphasize, how do you lower the splat factor? You could start by trying to lower the particle size or getting a better fineness from the pulverizer. Having high calorific coals or coals with lower sulfur and lower ash levels will help. And then of course anything that you can do to lower the velocity in that coal pipe, like reduce the primary airflow, or again that higher calorific value has the same impact as not having such a high velocity coming out of that pipe. So reducing the velocity of the pipe, the size of the particles, and the coal that you're actually delivering to the plant having low levels of ash and sulfur all help or minimize wall slag formation. I also wanted to suggest that I have seen wet coal cause wall slag problems in the past, and I had a tough time explaining why was water or how wet the coal was an influence on the slagging behavior. But I now know that wet coal has the same impact on the pulverizers as low calorific value coal. In other words, wet coal takes a higher coal flow rate and potentially more primary airflow to try to dry the wetness. And so wet coal actually influences the pulverizer performance and could potentially influence the splat factor and resulting wall slags. Another factor in the combustion aspects of a boiler that seems to influence the slag formation in the upper furnace is the side with the lowest oxygen, or if you have an O2 split, you have to worry about the low oxygen side, particularly if some of the oxygen probes are getting below 2 or 1.5 or even 1% oxygen, and then they average up to some higher number, but you have a zone of low oxygen. And usually the deposits are bigger on the side with low oxygen. This is caused by several reasons: the reducing atmosphere and potentially the higher furnace exit gas temperature as the flame looks for more oxygen. Here's an example of a split furnace, and they had low oxygen on one side and high oxygen on the other for a good average of 2.5% or so. But you can see what happened. That low oxygen side filled up with slag, and in this case from the bottom of the burner or boiler all the way up to the burners. The other side, the high oxygen side, had little if any deposits. I have tried to balance the airflows on a boiler numerous times to try to get rid of this O2 split, and I've generally been unsuccessful at doing that. And the reason why, I think now, is that the coal flow is imbalanced. And coal flow gets imbalanced particularly when you have a large amount of coarse material. Remember, the coarse material has the mass of carbon, and if it diverts to one pipe or the other, you're going to get more mass flow in one of the coal pipes. And the high side of the coal flow is usually the low side on the oxygen. In other words, the higher coal flow uses up the more balanced oxygen, so you get an O2 split. Sometimes it doesn't actually have to be a mechanical problem in the pulverizer, but here's a case where some mine debris has been caught up in the classifier section of the pulverizer. This caused a big pipe imbalance issue and was actually the root cause of a big slag problem where we had the unbalanced oxygen because of unbalanced coal flow, and here's the root cause being a coal quality issue, because I'm going to call that trash in the coal. So most coal contracts don't allow for trash in the coal, and here's a case where it actually caused a slagging issue. I've emphasized the air-to-fuel ratio in a pulverizer as being an important factor. In other words, if you put too much primary airflow in, not only do you cause potentially coarser material, you can increase the split. So here's some limited data on a pulverizer showing that. And so one of the things I'm asking you to look at is that primary air-to-fuel ratio curve in your boiler, and have you potentially biased it up, or where is your primary air-to-fuel ratio for your pulverizers? At full loading, it should be 2 or less. So if you're running over 2, pounds of air per pound of coal, or kilograms of air per kilogram of coal, or a ton of air to ton of coal, if you're running over 2 air-to-fuel ratio, you potentially could have too much airflow in there. So I'm asking you to look at that. And here's some evidence that the higher airflows from a mill, or when you jack up the primary airflow in a mill to higher air-to-fuel ratios, you deteriorate the sizing. So not only do you deteriorate the sizing, you potentially cause fuel imbalances in the pipe, creating an O2 split. To finish up, I want to emphasize the importance of fineness on a pulverizer. Unfortunately, it can be set up for different components of operating a boiler. You can have the fineness set up for good carbon. You could have the fineness set up for good slag control. And you could also have the pulverizer set up for long life or low maintenance, which means low pressures on the roller and bearings and journals. And you can make the mill last longer that way, but you might actually be causing a more expensive slagging issue in the furnace. So one of the issues with how to set up the pulverizers is that depending on where you work, you might have different opinions how to do it, and sometimes these are in opposite directions. In summary, the elements iron, calcium, and sodium appear to be the worst elements in the coal in terms of making slags, and if you could limit the amounts of those materials, you'll have a more forgiving slag. If you have to burn a high base or fluxing element type coal with low fusion temperatures and or higher slagging properties, you're going to have to pay more and more attention to the pulverizers, the combustion of the actual flame and combustion of the unit, and trying to keep those boiler water walls clean. We'll be talking about wall cleaning in another video. Right now we wanted to look at the combustion impacts and the fuel quality impacts. So thanks again for watching this short video. Please look at our website at coalcombustion.com for more articles about slag, or feel free to drop us an email.